All right, guys, today we got a little bit of end behavior and leading coefficients and degree of a polynomial. Start off our practice worksheet here with this. They gave us a bunch of expressions here, all in one variable in terms of x. Like there's no y's with it, no z's, just x's. Sure, some of them are squared and some of them are cubed or whatever, but they're asking us to find the degree and the leading coefficient. Well, the degree is, if you look at all the terms, it's the biggest exponent you got. So in this one, it's a little tricky because there are no x's in this one. That's why it's got a degree of 0, because it's 13 x to the 0th, and if you remember, anything to the 0th power is 1, so that's like 13 times 1, which is just plain old 13. The leading coefficient is whatever coefficient is right in front of that term, so in this case it would be 13. So way too easy, so easy that it's hard. It's got a degree of 0. Then this linear guy right here, if it's got two terms in it, well, this is the dude with the x's with it, and whatever exponent is on that, that is your degree, so that's a first degree polynomial. And then the leading coefficient is a 3. Whatever number's right in front of that term, right, that's our leading coefficient. So on this dude, you got some constants, you got some 3x's, and you got some negative 5x squareds. So the degree is the biggest exponent of that term, right? So that's a second degree polynomial, and the leading coefficient is that negative 5. And then here on this cubic, you got some x's, x squareds, x cubes. This is a third degree polynomial, my bad, because of that's the biggest exponent and the leading coefficient of 4. So a little bit of warm up here. And 1 through 6, they want to know if this expression is a polynomial in one variable. If not, circle the reason why. If so, state the degree and state the leading coefficient. So let's just kind of dive in. They got to be using one variable first of all, right? And there's 4 basic rules. If it's got one variable, I mean, obviously if it's got x's and y's and stuff like that, that's a definite no. But if they're all at the same variable, there's 4 rules. It could have no negative exponents. It can't have any exponents that are fractions or decimals. It can't have any variables in the denominator, and it can't have any variables underneath the radical. So if we look at number 1, yes, nothing but x's, all in one variable. Now, does it meet these 4 rules? Any negative exponents? Nope. Any exponents that are fractions or decimals, like rational exponents? So nope. No variables in the denominator, that's good. And you don't have any variables underneath the radical, like where you'd see like the square root of x or anything like that. So yes, this is a polynomial in one variable. Then they say find its degree and leading coefficient. Well, it's not necessarily typed in standard form, so you got to find the term with the biggest exponent on it. So that's got a degree of 4, and its leading coefficient is negative 2 in that case. So kind of a little neat one. First, we got to FOIL this guy out right here before we can answer any of these questions. So you can tell it's got one variable, right? So we can go ahead and say that's because there's no y's or z's or anything like that. So first terms times each other, outside terms times each other, inside terms times each other, and last terms times each other. Go ahead and combine like terms. Plus 13x minus 10. One variable, so far so good. No negative exponents, no fractions or decimals as exponents, no variables downstairs, and no variables underneath the radical. So bada boom, this is a yes. What is the degree? Boom, it's got degree 2 and a leading coefficient of 3. So if we try this guy, are they using one letter? Yep. And do all 4 rules pass? Yep. So that's a yes. The degree? Find the biggest dude. Sometimes we circle them, sometimes we underline them, whatever. Degree 8, leading coefficient of negative 4. Number 4, they ask if this is in one variable, and this is a big fat no. And they want us to circle the reason why. If we say no, because dude, that guy's got x. That term right there has x's and y's with it. So we'll say no to this guy. On the next one, are they using one letter? Yes, they are. Does it have any negative exponents? Nope. Does it have any exponents that are fractions or decimals? Nope. Any variables in the denominator? Boom. We got a variable downstairs, so that's a no. On this guy, it is not a polynomial at all if you have any of these 4 rules getting violated. And then the last guy, all one letter, all 4 rules pass right there. So this is the guy with the biggest exponent on him. He's got a degree 6 and a leading coefficient of -1. So this was a warm-up, and now what we did in class was we did a Desmos activity. So what you need to do is go to student.desmos.com, and your teacher should have emailed you a code for your class, right? So check your email. You'll end up pausing the video, and it's a little discovery lesson. It'd probably take about 20 minutes. And you'll end up doing 25 slides total on that thing, and in the first 15 it'll warm you up to where you can answer these questions. So you'll need this practice worksheet, so please give this video a pause, go to student.desmos.com. It's nice if you type in your last name first and then your first name, so I'd be Fun and Still, Jarrett, so that way when everyone's in class it's organized alphabetically, and get this activity done. So pause the video. Alright, so I hope that kind of gets you a little bit of knowledge into end behavior based on like the degree of a polynomial, if it was even or odd, and what its leading coefficient was. So you can have your chart already filled out. This is basically what it should be, right? Just to make sure we're on the correct page here. So we talked about this in class. They want you to make up an example that's got an even degree, so it doesn't matter as long as the degree is even. Like it could be a second degree, a fourth degree, sixth degree. You can have any other stupid terms that you want to. It doesn't matter as long as the degree is this and the leading coefficient is a positive number. What do they really care about? The ends of the graph. So if you notice from the Desmos activity, like both ends of an even degree polynomial with a positive leading coefficient, we're opening up. We don't care about what's going on in the middle. There could be all kind of twisty going on in the middle. It's like, but both ends we're opening up. So that's why I sketched the graph with its open space in the middle. So for a negative leading coefficient, boom, whatever you want, as long as you got an even degree and a negative leading coefficient, both ends pointed down. And we should be quite familiar with this based with our parabolas. You know, we know about that A value. Positive A value means it opens up, negative A value means it opens down, so we should be very, very familiar with that. But fourth degrees, sixth degrees, there's all kinds of crazy stuff that could go on in the middle of the graph. We care about the end behavior, so that's why we just, when I sketch those, leave that empty. And very similarly with the degree of an odd function, we're not as familiar with those though, but you should have noticed that the ends point different ways, like one points up and one points down. So that based all on the leading coefficient. So you got an odd degree and a positive leading coefficient. You know, there was all kinds of crazy language in that Desmos activity, but the phrase that I need you to remember is positive upright. If you have a positive leading coefficient and of course an odd degree, then as we go to the right, this thing goes up, like positive upright, like you're a positive upright kind of person, you know. People with a positive attitude are upright, you know, so positive upright. And that brings us to the last dude. If you've got a odd degree and a negative leading coefficient, then that's downright negative. So you know the ends are going different ways, and it's downright negative. Like if someone's an evil person, you're just like, oh, that person is just a downright negative dude, you know. So it's down. As you go to the right, negative. So just some phrases that I kind of remember. So alright, now to the back side. So we're done with the Desmos activity, and we'll just end up doing this. It's a big old honker chart about how we're going to write this end behavior. It talks about the degree being even and the leading coefficient being positive or negative and all that crazy stuff. We'll get into that as we do some problems down below. But what I'd like you to either highlight, underline, or circle is this other dude right here, this second category. The maximum number of zeros of a polynomial function is equal to the degree. So the number of zeros is equal to the degree of the polynomial. But here's the tricky part. On a graph, to count the number of real zeros by count the number of times the graph either crosses the x-axis or touches the x-axis. So here's the weird part. If the graph crosses, which we'll see some examples below, there is 1 0 right there. Like one of the zeros is there. All the x-intercepts are the zeros. But if the guy touches the x-axis, there is an even amount, usually 2, you know, we'll just for the sake of this, but when you get to college algebra, sometimes it could happen 4 times, 6 times, 8 times, whatever, but there's an even amount of zeros. For the intro level that we're in, we're going to say that there's 2 zeros right there. So holy crap, make sure this part is definitely highlighted or circled or something, put an asterisk by it, and let's go in and answer these questions. So we'll make that complicated chart much, much easier. For each graph, A, determine whether this is an odd degree or an even degree. Cool. Let's just do that right now. If this is even or odd, it's all about the end behavior, right? So it's about these ends right here, and are they going the same ways or different ways, right? Since these are going the same ways, doesn't that have an even degree in that? And to be quite honest, it doesn't ask for it, but the leading coefficient is also positive, right? Because they're both going up. So we'll ask those later this chapter, but hey, didn't ask it here, might as well ask it now. That's even degree because both ends are going the same way, and it's a positive leading coefficient because they're going up. But this part B, this is the funny part. Describe the end behavior. Sorry, I got interrupted there. So anyway, to do this end behavior, that's the weird part at first. So let's just kind of roll like this. All of these, once we get done with all 4 of them, it'll make a lot more sense, but here's how we'll start. As x, oops, that's not an x. How about as x approaches, we'll use this arrow, negative infinity, comma, f of x, that's the y value, approaches blank. And then the second line we'll do as x approaches infinity, comma, f of x approaches blank. So if we have this strategy to do end behavior, and we just set it up this way every time, it's really not that bad. Because remember, it's called end behavior. So what I like to do is always just call this end A and this end B. So you have an idea of what I'm talking about here. 2 ends, right? A and B. So the first phrase here says, as x approaches negative infinity, would you believe that these x values, -1, -2, -3, -4, -5, as we go to the left on the graph, right, that's where the x's approach negative infinity. So this guy is talking about your left end. Cool. The left end of these two is A, right? This is the end that's on the left side of the graph. They want to know where that's going. What are the y values doing in that? They're either approaching infinity or negative infinity. And baby, since this guy's going up, would you believe that those are approaching positive infinity? So boom, boom. Cool. Then we do that for the other end. As x approaches infinity. So that's this end right here. 1, 2, 3, 4, 5 for these x values. As you move to the right on the graph, all the x's are getting larger and larger and larger and larger. So as x gets bigger, as it approaches infinity, what is this end doing? What are the y values doing? Well, would you believe that that is also approaching infinity? And this should make good sense that they both went to the same place. This has an even degree, so the ends have to go the same way. They're both going up, right, to positive infinity. The y values keep getting larger and larger and larger. So, whew, cool. Alright, so we'll get used to that as we do the other 3, but now they ask to count the number of real zeros. Okay? And the real zeros are where this guy crosses the x-axis at, or even touches the x-axis. So let me get a red highlighter out here, and let's notice this. Here is a place where this guy crosses over the x-axis. Would you believe the graph, if I was to trace it, was above the x-axis? Now it's below, so it crossed over. So there's 1 there. Anywhere it crosses over, you get 1 actual 0. So 1 here. And then here's another one where it crosses over. So here's another one where it crosses over. Here's another one where it crosses over. Here's another one where it crosses over. And here's another one where it crosses over. All of these x-intercepts actually cross over the x-axis, so they just count once. So 1, 2, 3, 4, 5, 6 of them. This is a 6-degree polynomial, so 6. And that makes good sense, bada bing, because it's supposed to be even in that case, so nice. Let's try that again. First, they want to know if it's even or odd. Well, we look at the ends, and they are going different ways. So since they're going different ways, that is an odd degreed function. You can even tell, since that's going down as we go to the right, that's got a negative leading coefficient, right? That's downright negative. How about for the end behavior? We'll always start with this phrase, as x approaches negative infinity, comma, f of x approaches blank. And we'll do that same thing down here, but x, it doesn't go to negative infinity, it goes to positive infinity. So every single time when they ask you to describe the end behavior, we're going to start with this generic little dude. We're going to fill in the blanks. So there are two ends, A and B, and if x is going to negative infinity, that is the guy on the left, right? As this goes to the left, that's this guy. Where is this old boy going? He's going up, right? That's going up, so that goes to positive infinity. And as x gets bigger and bigger and bigger, that's going to the right end of the graph. Where is this guy going? He's going down, right? So that's going down to negative infinity. And because this was odd, bada bing, these guys have to go different. If one of them goes to positive infinity, the other one goes to negative infinity. And now let's go count the number of real zeros. The real zeros are where you either touch or cross the x-axis. This guy crosses over the x-axis, so they count once. So 1, 2, 3, baby. Bing, 3, ding. Perfect match, because that is an odd number of zeros in that case. So let's try again. Ooh, is this even or odd? Well, both ends, call this end A and this end B, go in the same direction, so that is even. End behavior, as x approaches negative infinity, f of x approaches blank. Same thing. As x approaches infinity, f of x approaches blank. This is the weird part when they're asking you to describe the end behavior. You know, this is what they want you to do, set up these phrases. And let's talk about it. This is your left end. Like if you do it in the same order I do every time, this is always the end on the left. This guy's going down to negative infinity. How about the guy on the right? This guy's going down to negative infinity. They're supposed to go the same way. This is an even degree. And now for the awesome part. State the number of real zeros. Well, it's where it either touches or crosses the x-axis. And this guy, he just ended up touching the x-axis, but he never ever crossed over. If I highlight this thing pink, I never ever went above the x-axis. It touched it, but never crossed it. So that means that there are actually 2 zeros at that case right there. So that is 2, which is a perfect match for an even function. And if you were just kind of curious, like if this was in factored form, it'd be like x plus 2 times x plus 2 equals 0. And they're like, oh cool, what value of x makes this 0? If x was negative 2, or if x was negative 2, like you get the same root both times. It's called a double root in that case. So when it just touches, truthfully it happens an even number of times, but for our sake we're going to say it happens twice. And then the last guy right here, let's see where the ends are going. So one of them's going up and the other one's going down, so that's an odd degree. As x approaches negative infinity, boom, f of x approaches blank. And as x approaches infinity, f of x approaches blank. End behavior, 2 ends, end A on the left and end B on the right. Where is the left end going? Down to negative infinity. Where is the right end going? Up to positive infinity. Those are going different places because this was an odd degree polynomial. And let's count our zeros here. There is 1 right here because this x-intercept, the graph actually crosses over the x-axis. So 1 right there, and right here, this guy just touches it, so that ends up having 2 x-intercepts there. So 2 here, 1 there, grand total of 3. Perfect match for an odd degree function because the number of x-intercepts tells you about your degree of that guy. So awesome, man. Hope you liked the Desmos activity. If you couldn't get that to work, let your teacher know. And if you have any other questions, let us know. Have a good one.